Assalamualaikum. We are from group 21 and today we are going to present our project which is aerodynamic flow on 2D car model using CFD methods. Next, this is the team members for this group. My name is Nur Alia Isa. I am the leader for this group. Our team members are Nazir Shafiq, Roslyn Rosli and also Muaz Haikal Maurad. For the problem statement, we have two problem statements, which is the first one is aerodynamic design, critical for efficient vehicles. High drag force increases fuel consumption, lowers performance, and contributes to pollution. So, drag force happens when cars move through air. More drags means the car uses more fuel and costs more to run over time. This also lowers performance and creates more pollution, which is bad for the environment. So, it is important for engineers to know how a car's shape affects airflow at different speeds. Even though car design have improved, many cars still have high drag. So more study is needed. Next, other problem statement is this study used CFD to analyze how different 2D car shapes and speeds affect drag, aiming to improve car design for better efficiency and environmental effect. So basically, we have used computational fluid dynamics or CFD to test simple 2D car shapes. It will look at how different shapes and speed change drag and other forces. The results will help show how better designs can reduce drag, save fuel, and make cars more efficient. In the end, this study will help the car industry build cars that use less energy and are better for the environment. Our objective for this project is to analyze the effect of changes between two types of 2D car body shape on drag force and airflow using CFD simulation, and the second one is to examine the relationship between four different airflow speeds and aerodynamic performance of each tested car shape. Next, for the geometry, mesh or grid and boundary used. For the geometry definition, the 2D car without a spoiler is a simple shape of a car. It has a curved front, smooth roof, sloped back and a flat bottom. The backs end straight on at the trunk with no extra part. But for the 2D car with a spoiler, it's the same shape but has a small flat plate at the end of the trunk. The spoiler sticks out at the back or a little upward. It is about 10% of the car's length or 2 until 5% of its height. The spoilers change how airflow and affect drag and lift. These simple shapes help compare how a spoiler affects the car aerodynamic in CFD test. Next, for the mesh or grid, the whole of the test section consists of two regions, which is external and internal. For the external, where mesh is less refined, it is consisting of coarse element, and for the internal, the mesh is more refined, consisting of fine element. Next, for the boundary condition, for our simulation, we set 5 key boundary conditions to accurately model the airflow around the 2D car shapes. First, the inlet is defined as a velocity inlet with uniform airflow at 4 different speeds, which is 20, 40, 60 and 80 meters per second, to represent various driving conditions. The outlet is a pressure outlet set to atmospheric pressure or zero gauge pressure, allowing the airflow to exit freely. The car body is set as a no-slip wall, meaning air sticks to the surface. This simulates real surface friction between the car and the air. Similarly, the tunnel walls are also no-slip to capture how airflow behaves near the top and bottom boundaries. Finally, the ground is a stationary wall with a no-slip condition representing the road surface the car will move on. These settings help us simulate realistic airflow so we can observe pressure distribution, drag force, and how the weight region forms behind the car at different speeds.
In this analysis, I examined the airflow behavior around the 2D car body without a rear spoiler using the ANSYS fluent. The simulation was conducted at 4 different speeds, 20, 40, 60 and 80 meters per second. The purpose was to observe how the air interact with the car surface and how weight region form behind it. From the velocity contour plot, it is clear that the airflow accelerates over the top of the car and then slow down significantly behind it, especially at higher speed at 20 milliseconds per second. The weight region is relatively small, but as the velocity increases, the weight becomes larger and more turbulent, particularly at 60 and 80 meters per second. This area is represented in green, indicate the low velocity flow, while the fast moving region are shown in the red. The streamline help to visualize the flow direction, and at a lower speed, they remain smooth with minimal disturbance. However, at higher speed, the flow detached from the rear surface, creating a noticeable recirculation zone behind the car. This is seen as circular swirling pattern in the streamline plot, which indicate the vortex forming due to fluid separation. This vortex increases pressure drag, reduce aerodynamic efficiently, and common in bluff body shape like a boxy car without aerodynamic aids. Overall, the results showed that without a spoiler, the car experienced stronger flow separation, larger weight region, and increased aerodynamic drag as speed increased.
So for my part, I will talk about streamline for car with spoiler. As we can see, I have 4 different velocity, 20 meter second, 40 meter second, 60 meter second, and 18 meter second. We can see the top left of the figure, the 20 meter second velocity have the greener color, which means the velocity is lower compared to the other where the color become much redness. From our ANSYS fluent analysis, we can conclude that the spoiler will generate high damp force as much as 10k Newton for 18 meter second compared to the car without spoiler that only have 500 Newton downforce for 18 meter second. We also found out that the higher velocity is the higher drag force. With the edges of spoiler, it make the drag force become larger. This be proof from our analysis. The picture show the blue color turbulence shape at the back of the car. The shape will become bigger when the velocity increase. That means the drag is also increased. At the end, the spoiler play the important roles to ensure the car become more stable, especially at the high speed.
This table summarizes the aerodynamic behavior of both car models at different speeds. At 20 meter per second, both models perform similarly. The car without the spoiler has smooth airflow and the spoiler causes only a minor disturbance, so the drag difference is small. At 40 meter per second, we begin to see a change. The airflow over the car without the spoiler remains streamlined, while the car with the spoiler shows a slight increase in turbulence, meaning the spoiler is starting to disrupt the flow. At 60 meter per second, the difference becomes more obvious. The spoiler-less car maintains steady, low drag flow. However, the car with the spoiler develops a noticeable wake behind it, leading to higher drag. Finally, at 80 meter per second, the spoiler significantly increased drag. The flow behind the spoiler becomes unstable, forming a large wake and a high pressure drag. Overall, this table clearly shows that the streamlined shape without the spoiler performs better, especially as speed increases. Based on our CFD simulation results, we observed that the shape of the car plays a major role in aerodynamic performance. The car without a spoiler had smoother airflow and a smaller wake, especially at higher speeds like 60 and 80 meter per second. In contrast, the car with a spoiler produced more turbulence and a larger separation zone, which increases drag. From the pressure contours, we also noticed that the streamlined car shape had more consistent pressure distribution, it helping reduce overall drag force. So overall, this confirms our hypothesis that aerodynamic shapes improve efficiency, while spoilers, if not designed properly, can increase resistance. This highlights the importance of balancing design for both performance and fuel economy. In conclusion, our CFD simulation clearly shows that car body shape has a major impact on aerodynamic performance. We compared two 2D car profiles, one with a spoiler and one without, across 4 airflow speeds, and the result proved that the streamlined shape without the spoiler consistently reduced drag and provided smoother airflow, especially at higher speeds. This supports our hypothesis and aligns with past studies showing that aerodynamic optimization is key to improving fuel efficiency and vehicle performance. Our study also highlights how CFD is a powerful and cost-effective tool for analyzing airflow, helping engineers design better and more eco-friendly vehicles. For future work, we recommend exploring 3D models and including other aerodynamic features like diffusers and underbody panels to get a more complete understanding.